Hello, I'm Regina Obe, and today I'm going to talk about the open source geospatial community, Postgres, PostGIS, and how PostGIS joins the two. So why would you be interested in this talk? PostGIS is one of the oldest extensions that's not part of the Postgres core. And over the years, it has built on top of what has been added to Postgres, and it has also influenced the direction of Postgres in terms of what it can do, which is later used for other extensions. So a little bit about me. I'm the president of a database consulting company located in Boston, Massachusetts, primarily focused on PostGIS and Postgres consulting. I'm also a member of the PostGIS core development team and steering committee, as well as some other geospatial projects. Over the years, I've co-authored several books with my husband on SQL, PostGIS, PG routing, and PostgreSQL. And I'm still working on 2 new books, which I hope to be done with next year. So what exactly is PostGIS? Well, PostGIS started out as a single Postgres extension, but over the years has expanded into several more extensions that are part of the PostGIS project. And there are many ways of pronouncing PostGIS. There's the way that I normally pronounce it, PostGIS, and for people familiar with geographic information systems, they might call it PostGIS. And it's also a play on the fact that it came from Postgres and that it is a successor to the GIS movement. And then there's another pronunciation, PostGIS, which I think is cute, but I rarely hear that one. So why PostGIS? Why did PostGIS even come to being? And the primary reason for PostGIS is to make spatial data not special. And to understand what that means, if you flash back to before PostGIS was created, there were some standards coming about that were reaching maturity. There was the Open Geospatial Consortium Simple Features for SQL, which later morphed into the SQL Multimedia Standard, which is now part of the ISO SQL standard. And along the way, numerous output standardized formats were produced that allowed for sharing of data between systems. The most popular of which is the well-known text and well-known binary, which pretty much every spatial database supports. And then in addition, PostGIS supports several others. Some of them are not geospatial. For example, the scalar vector graphics allows you to draw PostGIS vectors directly on a web browser. And then there's the X3D, which is a successor to virtual reality modeling language. So PostGIS was born 2001, as mentioned, to make spatial data not special. And what exactly that means. So in 2001, there were very few relational databases that supported spatial data. So the world was divided into the geospatial world, which used primarily desktops and files to distribute systems, and the relational. And when they needed to interact with relational data, they grabbed the relational data, they stuffed it into their desktop, and they produced these files. But there were some spatial databases around that time. There was Oracle Locator, which pretty much could only do distance. There was Oracle Spatial, which cost 4 times the amount of Oracle, but was really what you needed to do advanced spatial operations. And believe it or not, before PostGIS even came on board, Postgres was already a spatial database. It's even in the name, GRES. So GRES stands for Graphical Retrieval System, and its predecessor, Ingress, stands for Interactive Graphical Retrieval System. Presumably they removed the in because it wasn't that interactive. And the other relational databases aside from DB2 had no spatial functionality whatsoever. So at that time, everyone that was in the relational camp and needed to work with spatial data often migrated from the other relational databases, Oracle, SQL Server, MySQL. You saw quite a few people migrating from those to Postgres because of PostGIS. But PostGIS wasn't the only spatial extension for Postgres at the time. There was another that was around the same time called PGSphere. PGSphere was designed primarily for astronomical data, not for geospatial. And you might recognize some of the people that spearheaded that, Oleg and Theodore, who co-founded the company Postgres Pro, which much of the JSON-B and GIST and full text advancements have come through them. And at the time, PostGIS and PGSphere both had a great interest in improving the GIST support, and so they banded together to improve that, which later on was used for other extensions. But PostGIS, even though it was standards compliant, it would be nowhere without desktop tools to support it. And that was one advantage it had over what was built into Postgres, in that it had friends. And these were various open source geospatial projects that came together later to form a foundation called the Open Source Geospatial Foundation. So the most popular of these are GeoServer, MapServer, QGIS, and GRASS. So QGIS is started out as just a tool for viewing PostGIS data, but over the years expanded to view hundreds and hundreds of more, and it has a whole plugin extension system for people to hook in their various specialized workflows. And so if you look at what makes up PostGIS, it's got a couple of key features. There's the proj, which is the compass, and that allows it to transform between the various coordinate systems, which is very important for geospatial data, not so important for regular spatial. And then you have Postgres at the head, which allows it to interact with other relational data in the Postgres system. And since Postgres already built on standards and there are many drivers for it, it could easily interact with other relational databases. And then there's this other spatial components, Geometry open source library, which I'm a member of too, which is the engine that does most of the processing, like buffering and intersection and unioning that PostGIS is most known for. Then there's the Geospatial Data Abstraction Library, which is used by the PostGIS raster extension for reading various rasters and doing things like map algebra on rasters. And there's the Computational Geographic Algorithm Library, which is used to power much of the 3D functionality in the PostGIS SF-SQL extension. So those are all the pieces, but there's another project which is much bigger than PostGIS, and that is the OpenStreetMap project. And OpenStreetMap is a crowdsourced, think of Wikipedia except for maps, which aggregates work of hundreds of thousands of people to create a human-created map, as well as getting data from other governmental sources. And it started out storing their data in MySQL, but it did use PostGIS for tile generation for the map, the displaying of the maps on the web. And eventually, it decided that Postgres had more functionality and the transactional support was much better than MySQL. So they migrated all their data to Postgres. For editing, they don't really use PostGIS, but they use it for tile generation. And then there are other tools like Leaflet MapGL, which are JavaScript libraries, which can use the outputs like the GeoJSON that PostGIS provides or the Mapbox file. So you can use PostGIS even if you don't have like a mapping server. So I said spatial data is not special. And what do I mean by that? What I really mean is spatial data is not only special. Spatial data will always be special, but that doesn't mean that it can't benefit from the resources that a relational database can provide. And that's control of who has access to it, transactional support, and being able to use it from any language you want to use it from. So since PostGIS can speak SQL and it can provide pretty much all the standard spatial formats you can think of, you can tap into all its functionality with nothing but your basic .NET C, Go, or other languages that you're used to using. But if you didn't want to do all that plumbing, you could take advantage of the various desktop tools that have been created and map server tools that have been created to work with it. So here's an example PostGIS query. Find me the 3 closest roads, which looks like a pretty standard query, except for the less than dash greater than, which is the KNN distance operator. And that operator you'll see in other extensions such as PG Vector. And you could also do, if you're you're into demographics, you could do analysis with any arbitrary area, such as boroughs of New York, or even areas that you define and ask, what's the count of the various types of crime that have happened in that time? So even though I can't prove it, I would say that PostGIS, beyond affecting Postgres, also affected the wider relational database market, and even new databases, data warehouse databases, distributed databases. So, for example, before, there were very few relational databases that had spatial support. But now it's almost a requirement that all relational databases have spatial support. And you could see that in SQL Server, which adopted the SQLMM in 2008. And MariaDB and MySQL have been slowly trying to beef up their spatial. And even SQLite has many extensions. So there's Spatialite, which is basically a PostGIS but hooked into SQLite instead of Postgres. And you have the SQLite GeoPackage storage format, which is useful for distributing spatial data. And then you have CockroachDB, which is a distributed database that has a Postgres wire protocol compatible and SQL compatible interface. And it has built into it PostGIS. And then you have some other copycats. You have Alibaba Ganos. So they have a fork of Postgres, but they also provide, in addition to PostGIS, their own spatial extensions, which go beyond what the PostGIS raster, but the geometry is more or less equivalent. And so what exactly does PostGIS provide? Well, PostGIS provides 4 ways of modeling space. It has a flat, round, matrix, relational, which sometimes referred to as declarative because you declare that 2 things share an edge. So the flat model is the original model and the one that is part of the SQLMM standard. And it defines objects on a Cartesian grid. You can put 2-dimensional objects or 3-dimensional objects. So there's the 2.5D, which is basically a polygon with elevation, but then you can have true 3D, which are polyhedral surfaces, and triangulated irregular networks. And those are used for city modeling and landscape modeling. And then you have the geography type, which PostGIS kind of borrowed from SQL Server, but it's not really part of the SQLMM. And it has more or less the same subtypes as the geometry, except it's missing curves, which geometry has, and it's missing the advanced 3D formats, polyhedral surface, and tins. However, the objects are drawn on a spheroid or sphere, and the coordinates are stored in longitude, latitude, so they're easy for newbies who are just trying to feed their GPS data into PostGIS. And then you have another format, which is probably my favorite format, the PostGIS raster. And raster data is my favorite because you can think about it in two ways. You can see it as a pretty picture, or you can see it as a set of matrices that are overlaid on the same space. So it's kind of a paint by numbers way of doing it, and you can aggregate things to form polygons and other things. And it's very popular in elevation, soil, population. It's the final product of aerial imagery, of aerial flights. And then you have the PostGIS topology extension, which provides the topogeometry type. And that basically treats objects as if they were primitives. So when you create a new topogeometry, it creates lines, points, and polygons in your topology. And so anything you add later on either uses existing ones or builds on that. So it's easy declaratively to say these two parcels share the same edge because they share the same edge. They're pointing at the same thing. And this is very popular for cadastral work where you have to manage boundaries. You don't want somebody's property folding into another person's property, and you want your boundaries, like your county boundaries, to be completely collective of the state. And in addition to the extensions that are part of the PostGIS project that provide types, there's also ones that just provide extra functionality. So there's the PostGIS SF Seagull, which provides much of the processing power for polyhedral surfaces and tins. So you can ask things like, what's the volume? What's the surface area? Give me a 3D convex hull, things like that. And then there's the PostGIS Tiger Geocoder, which is used for geocoding or reverse geocoding U.S. data. And it utilizes U.S. Census Tiger data, which it provides a loader script for. And then there's the address standardizer, which is the first step to geocoding. You want to take your address and split it into its elemental parts, like the street number, the street, the postal code. And so that's what address standardizer does for you. And so if you look at the box that has PostGIS 3+, those are all the extensions that come with PostGIS. But there are other extensions that extend PostGIS that are not packaged with PostGIS, and those are separate projects. So there's the PG routing project, which I'm a member of also, and it provides network routing. Primarily, it's used for geospatial networking, for example, trip navigation, plane routing, train routing, bicycle routing. But it's really just a bag of graph algorithms, so it can be used for any problems where a graph that can be expressed as a graph. And then there's Mobility DB, which extends the PostGIS geometry types. to provide a temporal element. And one of the nice things about Mobility DB is it has things like a temporal speed, average speed, aggregates, so that you could quickly, using a group by or an SQL group by, ask for the average speed of a portion of the trip. There is OGR FDW, which is a spatial extension, a foreign data wrapper, but it can read more than spatial data. You can read a whole folder of CSVs, for example, and it will automatically interpolate what the structure is of those. So I think PostGIS will be around for a while, and it's going to always contribute to the movement of Postgres. And I think it's a good example of how other extensions can build on top of each other. Thank you for listening. And if you need to contact me, my contact is here.